Students, welcome to this lecture number 9 on thermodynamics. In this lecture, we are going to discuss a very important topic in this chapter, that is the second law of thermodynamics. Before going to understand the second law of thermodynamics, it is required to understand some drawbacks of the first law of thermodynamics. Because why second law comes, that we have to first understand. First law of thermodynamics is a very useful law, and it has correlated between the internal energy change of the system with the work done on the system, work done by the system, and the heat absorbed by the system or evolved by the system. This is a very useful law, no doubt. But this law puts no restriction of the flow of heat. But from our practical experience, we know that heat flows from the hotter temperature, means higher temperature, to the lower temperature. And this is a spontaneous process like other naturally occurring spontaneous process, like expanding of the gas in the available volume. Like when carbon is burned in the open air, it produces the carbon dioxide. All are spontaneous process and unidirectional process, that we need to understand. All the spontaneous process are unidirectional. You cannot find it otherwise. Means that we cannot find that heat flows from the colder body to the higher body. That cannot be found anywhere. Or the gas is contracting without doing anything in the corner of a container. That is not also possible. And carbon dioxide never going to produce the carbon and oxygen on its own. So these are all the spontaneous process and goes on unidirectionally. And this is the things, that is the subject matter, that is the brainchild of the second law of the thermodynamics that we are going to discuss in this lecture. So we can write closely related to the spontaneity of the reaction. This is K. Mukherjee in the Science with Mukherjee Sir YouTube channel. Now let us understand what do you mean by spontaneous process. When we talking about spontaneous process, things comes to our mind that as soon as the reactant comes in contact with each other, it will immediately react. But that is not the right concept of the spontaneous process. Spontaneous process is something other thing that slightly different from what we have a mental picture. That is, as for example, we keep some hydrogen and oxygen in a container at a room temperature and we leave this as it is for years. Do you see anything happens there? No perceptible change you will find. Because this is not because there is no reaction is going on between the hydrogen and oxygen. Reaction is going on, but it is in a very slow rate. So we will call this reaction a spontaneous reaction, although its perceptions, you cannot find much of significance of this. So how do you interpret, how do you define the spontaneous reaction? The spontaneous reaction we can write this is a process either takes place itself means that what want to mean that it will no need any external help. This is a process either takes place itself or by initiation. Or by initiation. Independent of rate. There is no relation between the rate of the reaction and the spontaneous reaction. Independent of rate. This we will call the spontaneous reaction. This is what? The spontaneous reaction. Spontaneous reaction or process. Process or reaction. So what is spontaneous reaction or process? This is a process that takes place itself without any help from the external agencies and or by initiation. And there is no relation between the rate of the reaction with this spontaneity of a reaction. And non-spontaneous reaction that takes place neither by itself nor by initiation. These are called the non-spontaneous reactions. And another thing we can understand for the spontaneous reaction, it is unidirectional, it is irreversible. You cannot reverse the course of its direction. Okay? So now we understand what is a spontaneous process. Spontaneous process is basically those which either takes place itself or by initiation, independent of reactions. Now question arises, most $1,000,000 question. What is that? The driving force. What are the driving force behind the continuous process? Driving force behind the continuous process. Behind the spontaneous process means what are the factors that is going to influence the spontaneity of a process. That we are going to understand now. For that we have to examine the process like flowing of the water from the hill, top of the hill to the bottom, or when we throw something, it will fall on the ground. And why it is so? This is also a spontaneous process. You can see, you will never found that water will flowing from the bottom of the hill to the top. That never happens. It always happens, it will goes from the top to the bottom. And that is why? Because there is a net potential decrease in the direction of the change. There is a net potential decrease in the direction of the change. That is why this has happened. And same analogy we can take for the case of the reaction. And we can say the spontaneous reaction or process will occur in that direction. We can write this here, process or reaction that can occur, reaction that can occur in the direction where the decrease in the energy observed, where the decrease in the energy. And that we have observed for many exothermic reactions. As for example, this exothermic reaction that we are very much accounted, that is that produce of NH3. Here the enthalpy change is negative, that is heat is evolved, means that in the direction of the reaction there is a decrease of the energy. In case of this reaction also you will find that HCl also you can find there is a decrease in the energy. So that is why they are spontaneous, because the reaction is going on in that direction where there is a decrease of energy. But this is okay, that is a very much a potential factor driving force towards the spontaneous reaction. But there are some reaction which is spontaneous but endothermic. As per this reaction you can see N2 plus O2. This reaction you can see this is the enthalpy change is positive. At that case what you will say? And it is continuous, endothermic. Here there is a increase of the energy instead of decrease of the energy. So in this case, that logic, that reaction will proceed in the direction where the energy decreases do not hold good. So we need to understand some factors that are going to impact in the spontaneity of the reaction, and that is that we are now again discuss. For that case, we will take a process which is having the zero enthalpy change. Enthalpy change is zero, and this process we will take, this is the isolated process where we have kept some gases. Now we are going to take an example where there is a change of enthalpy is zero. That is basically it is an isolated system. In a container we have kept some two gases A and B. In the left hand side A, in the right hand side it will be B, and there is in between there is a movable separator. What we need, we can able to remove it from these places. Now when we remove it, what is going to happen? These two gases will mix with each other and it will going to diffuse and make a homogeneous mixture. Now we examine the process. Before the removing of the separator, if we want to pick the gas from the left hand side, what we find? We will always 100% sure that it will be the gas A. In case of right hand side, we can, if we pick the gas, we are 100% sure that will be gas B. But what happens when we remove it and the diffusion process is carrying on? At that time, you will find that gas is mixed, and now we want to take the left hand side gas. Are you sure that it will be gas A? No, it will not gas A. It may be gas A, maybe gas B. For this right hand side also, you will also have the same problem. So this system has achieved after the diffusion a unpredictable one. You cannot able to predict the system now. So we can imagine, we can consider, we can conclude one thing, that for a isolated system, you can write this, for a isolated system, this tendency of the energy to be much more random or disorderness. For the isolated system, tendency of energy become random, or we can say disorderness or randomness. So in this juncture we come across one very important thermodynamics function, that is called the entropy. we now understand the entropy. Entropy is basically the measure of the disorderness of the system. This is a measurement of disorderness of the system. Measurement of disorderness, or we can say randomness of the system. Disorderness or randomness. Randomness of the system. So entropy is basically the measurement of the disorderness or randomness of the system, and it is represented by S. And at the standard state we call the S0. So what is entropy? Entropy is the measurement of disorderness. When we heat, suppose there is a solid, then we heat it. This is a solid, suppose. Then it will liquid. We will heat it. Suppose we apply some heat, and after that it will again we heating it and we will get the gas. So at that time entropy of the solid will be the lowest. So we can see that entropy is going on increasing because the disorderness is going on increasing. Randomness of the molecules goes on increasing because there is a lot of mobility between the particles. As we increase, as we giving the heat, there is a lot of mobility among the particles, and it will going to entropy is going to increasing. Entropy goes on increasing. And we can understand now that will be a major factor for the driving force. That is the major driving force towards the spontaneity. This is the entropy. Now, what is more important, the entropy change. How do we measure the entropy change? That is again we have to understand. Now, the change of entropy, the most important factor. Change of entropy, and that is been represented by entropy, represented by delta S. In a process, it is basically in a process the amount of heat absorbed or evolved isothermally or reversibly. We know the reversible process, already we understand, previous lecture. Reversibly, heat absorbed or evolved isothermally and reversibly, divided by the absolute temperature, T. That is giving the entropy change, that is represented by delta S, and it is Q. You will write isothermally and reversible like this, and by T. So this is the entropy change. The units of the entropy, let us understand. Units of entropy, SI units, it is joule per mole per Kelvin. CGS units, it is calorie per mole per Kelvin. Okay. So we understand the entropy, we understand the entropy change, how do we represent it, and this is all. Now we will understand the total entropy change. What do we mean by the total entropy change? Total entropy change is basically when we are going to say any process or reaction is spontaneous or not, we have to measure the total entropy. Total entropy, that is change, is given by, that will be right, total. It is given by this system entropy plus the surroundings entropy. Surroundings entropy. System entropy and surrounding entropy both create give you the total entropy. When the heat is, suppose, how do we measure the system entropy or surrounding entropy? That can be easily measured. When the heat is lost by the system, suppose Q amount of heat is lost by the system, that is given by this system, that is minus Q by T. Suppose T1, at T1 it gives the heat to the surroundings, and del surroundings, delta S to surrounding, that will be plus by T2. So this how we can able to measure the entropy change of the system and the surroundings, and total entropy change of the system and surroundings will give the total entropy change. The total entropy change is, that is the sum of this entropy change in the system and entropy change of the surroundings. Okay. For spontaneous process, spontaneous process, the total entropy change, the entropy change total, that is delta S system plus delta S surroundings, will be greater than 0. When it is less than 0, then it is non-spontaneous. For non-spontaneous we can write, for non-spontaneous, del S total will be less than 0. And another case, that is when the process or reaction is reversible, at that time delta S total, that is the delta S system plus delta S surroundings, will be equal to 0. So there is 3 cases we can see. And spontaneous process, as we discussed earlier, that is totally irreversible. Thermodynamically it is irreversible process. Now we are going to understand how we can able to measure a entropy. Suppose in a system the temperature is changing, from T1 to T2, volume will changing from V1 to V2, and pressure is changing to P1 to P2. At that time, what will be the entropy change? Entropy change will be given by this expression, that is Cv ln T2 by T1, ln is the natural log, plus R into ln V2 by V1, and another formula, Cp is T2 by T1 and R is P1 by P2. In this way you can have this expression, because in the numericals you have to use this formula. We will do 2 numericals, that will also clear to you. So how do we change the entropy of a 1 mole of gas, ideal gas? And this formula you have to use. And we know there is a different type of process. Suppose process is isothermal. In isothermal process, that is delta change of the temperature is 0. Isothermal process, change of temperature is 0. As we can say, isothermal process, delta S is equal to 0. That will be entropy change will be R into ln V2 by V1 for isothermal process. When delta P is 0, means isobaric process. Different process we have already discussed. Isobaric process, that is delta S is equal to isobaric, that it will be Cp, del P is 0, so this term will be omitted. Then Cp is equal to natural log T2 by T1. And for isoporic process, when V is equal to 0, this is isoporic process. In this case, delta S is equal to, isoporic when V is 0, V2 by V1, there is no change. So we can write Cv into natural log T2 by T1. And this will be very, very helpful to you. And lot of questions regarding this will going to come. This is a question that when 1 mole of an ideal gas is compressed into half its initial volume and simultaneously heated to twice its initial temperature, the change in the entropy is what? That we have to, option is giving, that we have to solve it. Previously we have already discussed the formula for this. So we know that here the volume has been volume related and the temperature is related. So entropy change, this formula we will apply delta S, that is Cv ln T2 by T1 plus R ln V2 by V1. Here you can see T2 is twice of this initial temperature. So Cv into Cv is, you know, the specific heat capacity into constant volume. T2 is given 2T21 by T1 plus R is equal to ln V is equal to V2. V2 is given by V1 by 2 by this. So we will get Cv ln 2, and this will be minus R ln 2, and this will be ln 2 will be common, and Cv minus R. This will be the answer. And so today we have discussed about the entropy change. That is, entropy change is one of the basic factors along with the enthalpy change, which is going to the spontaneous reaction behind the driving force behind the spontaneous reaction. Now the second law of thermodynamics can be expressed in the different ways. That we will go through. That all second law of thermodynamics is all continuous process is irreversible. The first reversible. All spontaneous process is reversible, thermodynamically reversible. Number 2, it is impossible to convert 100% heat into work. It is impossible to convert. We can write completely heat into work. Second. Third, the entropy of the universe is increasing. And fourth, total entropy change that we have discussed. Total entropy change is positive. These are all the 4 postulates, 4 findings we can say about the second law of thermodynamics. This is. So now we understand what is the gap between the second law and first law, and how do we able to say about the spontaneity of the reaction, what is the spontaneous reaction, what is entropy. Okay, I think that is all for today's lecture, and we will give next lecture we will discuss on another very important thermodynamics functions, that is the Gibbs free energy. Okay, thank you very much for watching. Okay.